Hi everyone, in this recording we will be going over section 3.9, differentials. After this video, our goal is that you will be able to understand the concept of a tangent line approximation, that you'll be able to compare the value of the differential dy with the actual change in y, delta y, that you'll be able to estimate a propagated error using a differential, and that you'll be able to find the differential of a function using differentiation formulas. In our previous section, we talked about Newton's method and how we can approximate the zeros of a function by using tangent lines. In this section, you will learn another technique that can approximate the graph of a function by using a straight line. So we let f be a differentiable function at c. The equation for the tangent line at the point c, f of c, is y minus f of c is equal to f prime of c times x minus c. Isolating the y, we have y is equal to f of c plus f prime of c times x minus c. Now as x approaches to c, the limit of y is f of c. So here's an example. We are provided the function f of x is equal to the square root of x plus 4, and we are told to find the linear approximation, or the tangent line, at the point 0, 2. So then we will construct a table to compare the y values of this linear function with those of f of x for the x values near 0. So the first step is to differentiate the function f. So f prime of x is equal to 1 divided by 2 times the square root of x plus 4. So the equation of the linear function at 0, 2 can be given by this approximation, so the definition we just went over in our previous slide. So y is equal to f of c. In our case, c is 0 because we are choosing values near 0, plus f prime of c, where c is 0, so f prime of 0, times x minus 0. So in our original function, f of 0, we get, plugging in 0 for x, we get the square root of 4, which is 2. Now f prime of 0, so plugging in 0 right here, we get 0.25, and then x minus c, and so this term will just vanish, and we'll be left with 2 plus 0.25 times x for our linear approximation. So for our first column, right here, we're choosing x values near 0. So we have negative 1, negative 0.1, negative 0.01, 0, 0.01, 0.1, and positive 1. Now we are evaluating our original function at these x values. So f of negative 1 is equal to the square root of 3. F of negative 0.1 is equal to the square root of 3.9, and we keep on going. Now we are evaluating our approximation function at these x values. So the function we just defined right here, 2 plus 0.25x, and plugging in negative 1 for x right here, so we get 1.75, and then plugging in all these values for these respective values right here. Now here's our error, so the difference between the original value from our function minus the approximation value from our approximation function. And we're taking the absolute value. So we see that the error decreases as we get closer and closer to 0 from both directions. So that means that the linear approximation of f at the point 0, 2 provides accurate values near x is equal to 0. So this line gets accurate when we approach x is equal to 0 for our function f of x is equal to the square root of x plus 4. When the function y is equal to f of c plus f prime of c times x minus c, or in other words our tangent line, is used to approximate the graph of f, the quantity x minus c is a change in x, and it is denoted by delta x. dx is the most traditional denotation. So delta y is equal to f evaluated at c plus delta x minus f of c is a change in y, and its approximation is f prime of c delta x. So we let y equal f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number. The differential of y, denoted by dy, is equal to f prime of c dx. So here's an example where y is equal to the square root of x, and we are told to find the value of dy when x is equal to 4 and dx is equal to 0.5. We are then told to compare this value with the exact value of delta y for x is equal to 4 and delta x is equal to 0.5. So because y is the same thing as saying f of x, then we have f of x is equal to the square root of x. Now the first derivative of f of x, f prime of x, is equal to 1/2 times x to the power of negative 1/2, so using the exponent rule, and that is equivalent to 1 divided by 2 times the square root of x. So the differential dy is calculated as f prime of x dx. So we are told to evaluate when x is equal to 4 and dx is equal to 0.5. So we plug in 4 in our first derivative, so f prime of 4, and delta x was 0.5. So f prime of 4 times 0.5. So we have 1 divided by 2 times the square root of 4 from our first derivative, evaluating at 4, times 0.5, and that is equal to 0.125. So this value, dy is equal to 0.125, represents the change in the y value along the tangent line. To find the actual change in the function, delta y, for the same interval, delta x is equal to 0.5, we calculate delta y. So that is equal to f of the original function evaluated at x plus delta x minus f of x. So x was equal to 4, delta x was equal to 0.5, so 4 plus 0.5 is equal to 4.5. So we will be evaluating our original function at 4.5, so we have f of 4.5 minus f of 4. So that is equal to the square root of 4.5 minus the square root of 4. And we can see that the two values are very close. So delta y is equal to approximately 0.12132, the exact change, and dy is equal to 0.125, the approximation. So the differential dy provides a good approximation for delta y. So as you try smaller values for dx, the two values will become increasingly similar, as shown in the graph and the following table. So the equation of the tangent line to the graph of f of x, where f of x is equal to the square root of x, at the point 4, 2, can be given by this function right here. So here we have y is equal to f of c plus f prime of c times x minus c. So in our case, the c is equal to 4. So we evaluate our function, our original function, at 4. So the square root of 4 is equal to 2, which is what we got here. F prime of 4 right here is equal to 1/4, and then we just leave it as x minus 4 right here. Now distributing this 1/4 and then combining the 2 and the 1, and then negative 1, we get that y is equal to 1/4 times x plus 1 as our tangent line. So this will be our approximation. So now we choose x values near our c, it's our 4. So we have 3, 3.5, 3.9, 4.1, 4.5, and 5. Right here we will be evaluating our original function f of x at each of these x values. And then for this third row, we will be evaluating our tangent line at each of these values. And then our last row would be the error. So the original function evaluated at each of these values minus our approximation function evaluated at each of these values, and we're taking the absolute value. So we see that as our x values get closer to 4 in this direction, the error gets smaller and smaller, but then it gets bigger right here, and then it goes back to being smaller. But it is most accurate from these values. At x is equal to 3.9, we had an error of 0.001. In physics and engineering, the approximation of delta y by dy is commonly used to calculate propagated measurement errors. So we let x be our measured value. We let x plus delta x be our exact value. We let delta x be the measurement error. And we let delta y equal to f of x plus delta y minus f of x be our propagated error. So in this example, we are given that the measured radius of a ball bearing is 1.2 centimeters, as shown in the figure to the right here. The measurement is correct to within 0.02 centimeters. So we are told to estimate the propagated error in the volume of the ball bearing. So the formula for volume of a sphere is given as v is equal to 4 divided by 3 times pi r cubed. We're given the radius of the ball bearing, so that's 1.2, so r is equal to 1.2. And then our possible error, so we said that the measurement is correct to within 0.02 centimeters. So delta r will be in between negative 0.02 and positive 0.02. So to approximate the propagated error in the volume, we will differentiate v to obtain the derivative of v with respect to r is equal to 4 times pi r squared. And we will write delta v is approximately equal to dv. So we will rewrite dv by multiplying dr to the other side, so we will isolate the dv. And now we will have dv is equal to 4 pi r squared times dr. Now substituting what we have for r and dr, so r is equal to 1.2, we will plug that in here. And then for dr, we will put plus or minus 0.02 from right here. and we get that that is equal to plus or minus 0.1152 pi. So this is the calculated value in terms of pi. And then the decimal approximation is approximately plus or minus 0.36 centimeters cubed. So the volume has a propagated error of about 0.36 cubic centimeters. So all the differentiation rules discussed in Chapter 2 can be expressed in differential form. So if we let u and v be differentiable functions of x, then the following rules still hold. The constant multiple. So if we're multiplying our function by a constant, then the derivative of that constant times the function is equal to the constant times the derivative of the function. Now for our sum or difference, if we're taking the derivative of the sum of two functions or the difference of two functions, that is the same thing as taking the derivative of the first function plus the derivative of the second function, so for the sum. And then for the difference, we have the derivative of the first function minus the derivative of the second function. Now our product rule carries over, so if we have the derivative of the product of two functions, so u times v, that is the same thing as saying u times the derivative of v plus v times the derivative of u. And then lastly, our quotient rule. If we're taking the derivative of u divided by v, that is equal to v times the derivative of u minus u times the derivative of v, all divided by v squared. So here we have some examples of finding the differential of a composite function. So for our first example, example number 4, we have the original function y is equal to f of x, and that is equal to e to the power of 2x. So f prime of x is equal to 2 times e raised to the 2x. So we applied the chain rule. Now in differential form, dy is equal to f prime of x times dx, and that is equal to 2e to the 2x times dx. So we just plugged in our f prime of x right here, and then our d of x for dy. Now for example 5, we have finding the differential of another composite function. So we have y, and that is equal to f of x, and that is equal to 3x squared minus x, all raised to the power of 5. Once again, we apply our chain rule, and we get that f prime of x is equal to 30x minus 5 times 3x squared minus x, all to the power of 4. So dy is equal to f prime of x times dx. So f prime of x we just found right here, and we plug it in right there, and then we multiply it by dx for our dy. So for our last example, we are using differentials to approximate the value of sine of 29 degrees. So we let f of x equal sine of x, where x is in radians. First we differentiate f to obtain f prime of x, so the derivative of sine of x is equal to cosine of x. Then we use f prime of x is equal to the derivative of f with respect to x, and that is approximately equal to delta f divided by delta x to write the differential approximation formula. So we have f of x plus delta x is approximately equal to f of x plus f prime of x dx. So plugging in everything that we have sine of x plus cosine of x dx. So now we will obtain a useful approximation by choosing values for x and dx based on the known sine values. So we know that sine of 30 degrees is equal to sine of pi over 6, and that is equal to 1/2. So we let x equal 30 degrees, which is equal to pi over 6 in radians. And delta x is equal to dx, and that is equal to -1 degrees. So we must convert delta x to radians to use it in the differentiation formula. So dx is equal to -1 degrees, which is equal to negative pi over 180. So f of x plus delta x is equal to sine of 29 degrees, and that is approximately equal to sine of pi over 6 plus cosine of pi over 6 times negative pi divided by 180. So just plugging in everything that we just found. And that is equal to approximately, or it is equal to 0.5 minus the square root of 3 times pi divided by 360. So using that the square root of 3 is approximately 1.73205, and pi is approximately 3.14159, then we get that sine of 29 degrees is approximately 0.484885.